the quiz I actually did on the board. This, but the entirety of that problem on the board. I think beta was different on the board, but that beta just, it's omega over c in free space. And everything fell apart after that. So, what I'm going to do now is I'm going to start with a dipole, infinitesimal dipole, get the electric field and H field from it, and then talk about, and I'll do the magnetic vector potential, but then I want to do something after. I want to talk about arbitrarily long dipoles. Then the biggie is the half-wave dipole that's so important. This is going to be a short dipole. And when you have a short dipole, what do you mean by short is the first thing. So it means the length of the dipole is less than lambda over 10. That's the standard definition. Now I want to tell you something. The way they do it in the book, there's something that is not quite right. They're using this, they're going to do it this way for a reason though. So they're assuming this has a current I naught on it. And the current does not vary versus the position. This will be the z-axis. It'll be located at the origin. And if you were to plot the magnitude of the current versus z, you would see it looks like this. So it has a value of I naught uniformly from the top to the bottom. Y'all follow me? Now, if you assume that current and you come a distance r away, and the angle here is theta, then what you end up getting is a magnetic vector potential here that is AZ, associated with this infinitely small, this short dipole, not infinitesimally small. And this value of AZ would be equal to mu 0 in free space over 4 pi, and it's the magnitude of R here. And then it's times the length L times I naught, which is the current. Then it's going to be times the actual e to the minus j beta r, and it's in the AZ direction. Now usually what I do is make this infinitesimally small, but Whitmore's book doesn't. He uses L here, because that way this will be a differential A instead of an actual value of A, because now the length is finite but it's short. After that point, normally they take AZ and they say it's equal to the actual value of cosine of theta AR minus the sine of theta A theta. Do y'all remember me doing that for AZ? So they're going to take the vector AZ and put it in terms of unit vectors and the radial and theta axis. Y'all, phi and theta and R. Y'all with me, class? Now if you take this and put it in here, you're going to get AZ, or A, you can just leave it as A at this point, is equal to mu 0 L times I naught all over 4 pi. The way I like to do this is break all the constants out to a single term. With me? Then after that, the next thing, get it a function of R. The next thing is e to the minus j beta r over r. And I'm using capital, but small r is appropriate too. It's just a radial measurement from the origin. This dipole is located at the origin, and it's oriented in the z direction. Constant magnitude. That's just a function of r. And the next function is going to be e to the minus, the next function is going to be this stuff, which is going to be cosine of theta AR minus the sine of theta sine of theta A theta. Now remember, A theta and A phi, or A theta and AR, pardon me, are unit vectors. Now here's what I used to do and what Whitworth did, and a lot of people do. At this point, that magnetic vector potential makes no assumption about near field, far field, or anything. You all with me? So normally what they do is they're going to say, okay, now remember that B is equal to the curl of A, and B is mu H is equal to the curl of A. So that means the H field itself, the entire H field, near field and far field, would be curl of A over mu. mu 0. In the back of your book, you're going to see that the curl of A is defined, and I don't even know the page, it's on the very back cover. And you're going to see things where you're going to have derivatives. This is in spherical coordinates. Derivatives with respect to theta, with respect to phi, and with respect to r. Do you all see that? Well, you see it, right?
Yes.
Now remember, that makes no assumptions except that the current is constant over that different, very small length, right? So when you do the curl, and this is in spherical coordinates, he does it. So I gotta say this. There is no dA of anything d phi. I hope you understand that. It doesn't matter if it's r, theta, or phi. There is no a component. I mean, there is no function of phi over here. Do you all see this, class? My point is, if nothing is a function of phi, all the derivatives with with respect to phi have to be 0. So now you come over here, and here's what happens for this, for spherical. You get 1 over r, and then he's going to have 1 over the sine of theta, dAr d phi. That one's going to go away. And he's going to have minus ddr of r times a phi. And then finally, and this is going to be in the a theta direction. I'm just going to do this. This thing is going to go away. So this would be the theta component of the curl. And then you're going to get plus 1 over r, and it's going to be ddr of r times, or minus dd theta, pardon me, of ar. This whole thing is going to be in the a phi direction. This form of the curl I don't use very much. Now here's the deal. With this one, when you look over here, is there any a phi term over here? Just take a look. There's only 2 terms, ar and a theta. Y'all see that? So that means the derivative of ar with respect to phi, this one goes away entirely, just by inspection. Y'all see this, class? Next, when you look over here, there's an a phi. Is there any a phi over here? Any vector over here in the phi direction? No. This goes away. Important to note that. Now we come over here. And take a look at this. Is there an a theta? A theta means the coefficient of the unit vector theta, and there is, right? You'll notice that this is something that's a coefficient of theta, right? And you can also see for a theta, I also have all this, right? I mean, it's this times all that. The AR coefficient doesn't exist. When I take a look at this, here's where I'm going with this. This part of the derivative, you all with me? So I'll put it down there, so it's 1 over r, 1 over r ddr of r times a, and this is going to be a theta. All right, so that's 1 over, you can use small or large, ddr. I'm going to put the r in. Now we need a theta. You notice that I'm going to do this too, and I suggest you do this when you have, if and when you have to do this. Make that a constant k. Just call k equal to mu 0 L I naught over 4 pi. And the reason I'm going to do that is because now the derivative I'm going to take is k times the function of r times that sine theta. So this is going to be times k times, and then this function, e to the minus j beta, I'll use a small r here, over r, right? And then it's going to be times a minus sine of theta, and that is the a theta. I have an r here and here, it goes away. Can you all follow me? And remember, I'm just doing this part. I keep looking at this. This is a DDR. The k and the minus sine theta don't matter. So I get minus the sine of theta over r times k out the front. And then I take a derivative of this with respect to r. It's e to the minus j beta r. That brings out a minus j beta, right? So it makes that plus, and it's times j beta here times e to the minus j beta r. So that's this derivative right here. Then I have to take dAr d theta, because I'll piece it together over there, but I'm going to do the individual derivatives separately. If you look over there, I need the AR. That just means whatever is a function of whatever has a coefficient of AR. So it's this term, y'all see this? Times all this stuff. And you'll notice the derivatives with respect to theta. A lot of the time, you don't see the importance of this, but you will later, because in the real world, you got to do a lot of manipulation with formulas to adjust them. I always do this. I put that as K, but when I look at this term, the sine theta there, I need the coefficient of, I need the coefficient of AR, so it's this, and then it's all this stuff. And really, I have simply, I need a d theta of AR, which is going to be K, right there. And it's e to the minus j beta r over r. Then times cosine of theta. I think everybody follows me this, right? When I do a derivative of this, what do I get? Well, the k and all this stuff stays there. So I get k, and I get e to the minus j beta r over r, and I get a derivative of cosine theta with respect to theta, which is minus sine theta, so this is going to be minus the sine of theta. Now I come over here and I put it all together, and I'll do it up here. So now I have curl A, which is equal to mu h. That's going to be equal to the first one, which is sine theta over r times k times that k, which is the I naught business, times j beta and times e to the minus j beta r. And then I get the second term, which is going to be k over r e to the minus j beta r times sine theta. And this is all in the AP direction. One of these terms should be r squared, and I'm looking at it. Trying to figure out.
You had those r's canceled first.
This r does.
Yeah.
Cancels, but there's still 1 over r here. Yeah. And I'm looking derivative of
Oh, the r squared is under k over r squared because there's another r in the AZ formula. Where 4 pi r, that r doesn't get canceled out. So that
wait. Hold. Where are you looking now?
so the r's
Are you looking on the board or not?
yeah.
This formula?
The if you go up,
Here?
yeah, that r, that
What
one.
r?
That's
This?
yeah.
Because it's right here.
Okay. Yeah, and where is it on this? Would it be r squared or on that?
Well, I mean, the way the formula is written, if you look, unless I did this formula, r times a theta, right?
Yeah.
Gets rid of the r downstairs. Then you take a derivative of that with respect to r.
I think it's the same one.
There's something that it should be, there should be a
If
1
you're
over.
taking a derivative of the respect to R, why is there 1 over R on the outside of the rim? Wouldn't that be part of the rim?
This is scale here. If you look at the depth, do you have your book? I'm going to check this one when I get done. Normally there's 1 over R squared here, that would be the near field term. I'm just going to tell you that then there's going to be the far field term. And I'm not sure if I wrote that derivative or the curl down wrong. I may have copied that thing down wrong, or it may be wrong in his book. But I know there's going to be a 1 over R squared term that's the near field term. I'm going to stop there. Maybe I'll ask you guys to do this for some credit. It's not a hard problem. It's done on the internet all over. But anyway, let me just tell you that it should have popped up with a 1 over R squared somewhere in there. But, and apparently, let's do that curl wrong. I mean, I think I might have stated the curl wrong. It may be wrong in the back of this book, now that I think about that.
Where is it in the back?
The very back cover, you'll have curl defined in spherical coordinates. It may be wrong there. Normally with these things, I do it in terms of a matrix definition. It's really the determinant where you have like AX, AY, AZ, DDX, DDY, DDZ, and then A sub X, A sub Y, and A sub Z. Let me get to the guts of it. Trust me on this one, if you actually did this right, apparently I didn't, you would get yourself a value of H that is a function of 1 over R squared, and a term that has just 1 over R. As a matter of fact, in his book, I know he shows that somewhere in the chapter. But here's the thing we're going to talk about. If you have this antenna and it's short, and the length of the antenna L is less than lambda over 10, and we're assuming the current on this thing is constant, I naught, then if you're at an angle theta at a distance r, and you're in the far field, so if this distance r is greater than lambda over 2 pi, then this is far field. I know you haven't had a lot of exposure to far field, but it becomes a very important concept. We're in the far field, the electric fields at that point and the magnetic fields are radiating. They're not energy you can get back. That's basically the demarcation. If you're at this point, what you're going to find out is you're going to get an E field. This you write down, it's in the book. You're going to get an E field from this constant current short dipole. Let's put this short dipole. That E field is going to be given as J eta beta I naught times L, and I'll have a 4 pi here, and then you can break out the E to the minus J beta R term here over R, and then it will be a function of sine of theta in the A theta direction. Now that would be the E field in volts per meter. 446, equation 8.61. It has a corresponding, this is a propagating field, this is in the far field, make sure you understand that. It has an H field. How would you get the H field if you have the E field in the far field? Simply divide it by eta, right, and then reorient it so that E cross H would be the direction of propagation. Which way is the wave propagating, by the way? It's got to propagate away in the AR direction. If it's at the origin, it has only one choice, R, if it's a propagating field. So the H field is going to be the magnitude of that, but it's divided by eta. You'll notice you got an eta up top, so here's a J beta I naught. You can divide by 4 pi times L, and you can put the same phase, the minus J beta R, same variation with R, divided by R, and then it'll have the same sine of theta variation, but instead of A theta, it's going to be A phi. And that would be amps per meter. This is in the far field. The two have an identical signature. One's oriented in the vertical axis, or I should say the theta axis, the E theta axis. The other is in the phi axis, the orthogonal. They're propagating the R direction. Now, the power density is the next thing I need to get. We're in the far field for this one. But if we're in the far field, then we are in free space, right? then the power density, P ab, this is oftentimes given as the symbol S, and this is called a Poynting vector. That's very common. They use this. This is S ab, the average power density is given as 1/2, and you can do it as the magnitude of E theta squared over eta naught in the AR direction, or you can give it as this way. Either one is acceptable. 1/2 eta naught times the magnitude of the H field in the phi direction squared in the AR. The units will be watts per meter squared. Either one of those two works. If you do the latter, you would get 1/2 eta naught. Now we got to take H and square it. Here's H, and you'll notice what happens when you square it. You're going to get a sine squared, right? And remember, it's magnitude, the E field or H field, so that phase term goes away. So you basically get this. You're going to get beta I naught L over 4 pi. This has to be squared. Then you're going to get 1 over R squared term. And you're going to get a sine squared term. I hope you understand. The only thing I'm doing is taking the magnitude of that thing, squaring it, multiplying by eta naught. The reason I did it this way, remember, E itself in magnitude is eta times H, right? Follow me on this, guys? So if you do that and put eta times H, I'm sorry, if you take E field itself and make it H times eta, you can see you're going to end up with this formula. Trust me, it does work. Come over here now. The next thing I'm going to do is say, this is in the AR direction. And the units are watts per meter squared. So if you look at this thing, the average power density, you can see it's a function of sine squared. And this is the average power density. Here's where we can play games. Everybody, you can see this all the time. What I'll take a look at is what can I get out of here to try to condense it down to something a little more manageable possible. If I look at this, I can take the I squared and the I naught L squared out in front. And the reason I'm doing that is because that's really a weight of how strong, you might say, the source is. It's proportional to L, proportional to I naught squared. Follow me? Now, the next thing I'm going to do is see if I can knock some of these constants out. He does this in the book. Well, I've got eta naught here, and I got a 2, so that's 1/20 pi over 2. You all follow me? Class, you with me on this? I'm just trying to reduce the complexity. Now I have beta over 4 pi. Right? Well, beta is 2 pi over lambda, correct? 2 pi over 4 pi is 1/2, right? So this beta is 2 pi over lambda, correct? I take that, divide by 4 pi, I get simply 1 over 2 lambda, correct? And then if I square it, I get 1 over 2 lambda squared, or 4 lambda squared, doesn't matter. Got the I naught L out in front. Then I'm going to have the functional variation with theta and R. So then I have sine of theta over R squared. I'm going to show you one last thing. This would be in the AR direction. I see this done all the time, so I'm going to show you something. You see how there's an L here, squared, and there's a lambda squared. I'm going to take the lambda out here, and you'll see this. You'll see L over lambda squared. Let's see, L over lambda squared, and then you'll have I naught squared over here. We can still reduce it further, right? You can see what, you can see I'm getting to a point where it's becoming obvious what I'm about to do. So this is really 60, right? Then I got 4 squared. I got 2 squared, which is 4, right? So this is what, 15, right? So that's 15 pi. This is in the book. 15 pi, 15 is pi squared. Pi squared, correct? 15 pi squared, I naught squared, L over lambda squared, sine squared theta over r squared. That's a 4.
So where did the squared pi? This
Beta is 2 pi, right?
But we got rid of that pi. We got rid of the 2 pi with 4 pi. That's how we got 1 over 2
Oh, I'm sorry, it's
squared.
Wait a second now. Beta naught, hold on. This is going to be one of those. I think pi is, let me see where I got it. When I look at this one, I'm just going to write it out here. So I have beta naught 120 pi divided by 2. Then beta and 4 pi. So beta is 2 pi over lambda divided by 4 pi is going to be 1/2, and I'm going to square it's 1/4. Then I got the lambda squared. I got L over lambda squared. Got I naught squared. What about here? It's 60. Maybe I'm wrong. Maybe it is just. I guess it is just pi. You see this in your book? The power density. So this should be P half in your book. And it has to be a function of r squared and sine squared. The next thing I want to get is I want to get the normalized power density with me because I'm after gain or directivity. So over here, what's the normalized power density one of you guys? Well, you take a look at this and really, it's what? This functional form. You got to find out where it's a maximum for a given r. Remember, the normalized power density will be a function of the angle. Y'all follow me in this class? Will not be a function of r. When you look at this or anything else, that's a sine squared operation. Sine squared has a large value of 1. That's it. So you can see that the normalized power density should be sine squared. Can you all follow me in this? That's the normal. Now we have normalized power density of this one is just equal to the sine squared of theta. Now, if we want the directivity, D, and this is maximum directivity. This is like right out of the quiz, isn't it? Now you can say that's equal to 4 pi, integral from 0 to 2 pi, the integral from 0 to pi of sine squared theta times sine theta d phi, correct? When all is said and done, you're going to find out that this is 3/2. Remember doing this? That's the directivity max. That means the actual directivity is a function of theta and phi. It's going to be d max, or really 3/2 times the sine squared of theta. Now we have the directivity. So I need the total power radiated. And what I'm about to do is this. Well, I need P rad. So P rad. I ask these questions, by the way, on exams. Ones with like, I will give you an electric field or a magnetic field. It's in a far field. And I'll ask you for the total power radiated because you're going to have to find the radiation resistance. You know, with me? So to calculate total power radiated, you would take the average power density, right? And what you would do is multiply, that would be the average power density, by the differential surface, and then you would have to integrate it over all space. That's the idea behind it. Now for our case, I'm going to try to do this right here. We had an electric field equal to J eta beta, and then it's going to be times L I naught over 4 pi e to the minus j beta r over r times the sine of theta, and that's in the a theta direction. What I'm going to do is try to use this, get it down, condense it here, and then square it divided by eta naught, see if I can get this thing manageable. When I look at this, and I look at the value first of the magnitude of E, and I'm going to start putting in constants. So I have eta beta. You think about this, eta times beta, and this is done all the time. These are things I work in this area, I do it all the time. Eta technically is the square root of mu naught over epsilon naught if you're in free space, correct? And beta technically is omega times square root of mu naught epsilon naught, right? You see how the eta naughts cancel? That square root of eta naught downstairs, eta square root of eta. But I get mu naught, right? And I get omega. Mu naught is 4 pi times 10 to the minus 7, and omega is 2 pi times f, correct? All right, now there's eta beta. I'm going to put them down, hopefully we'll get somewhere. So I got 4 pi times 10 to the minus 7, and then I got this times 2 pi times f. It's divided by, I took eta beta and I put it there, and I'm only worried about the magnitude. Then I divide this by 4 pi. I still have to worry about L and I naught. Now it's magnitude, so I don't care about the other term, but then I get the sine of theta over r squared. You can follow, or not squared, but it's magnitude, so I get this. You all with me? I didn't square anything yet.
Shouldn't I not be in the top?
It's on me. You're absolutely right. It's L times I naught. I'm going to cancel the 4 pi's. So at the end of the day, I have the magnitude of E that I will use from here. I'm going to take it down further. It's going to be equal to 2 pi times 10 to the minus 7, then times F times L times I naught, and then sine squared, or sine of theta, pardon, over R. Now I get the power density, yeah, 1/2 magnitude of that E squared over eta is 1/2 eta as 120 pi here, and then E squared. So it's 2 pi times 10 to the minus 7. It's going to be this squared times f squared times L squared I naught squared. And then I get sine squared theta r squared. Now what that tells me is the actual P max is going to be all this. Let's see if we get there. You follow me what I'm doing. I'm just trying to get this thing down to reasonable. If I look at this,
This is 8.81.
that,
Or the condensed term.
oh, he's got that. The entire thing is just a constant. I mean, maybe he does. So let's see what we got here. I got 1/2. Then I got 2 pi squared, 125. I got 10 to the minus 7 squared, is 10 to the minus 14. I got f squared, L squared, I naught squared, and then sine squared of theta over r squared.
I think I lied.
That's all right.
Yeah.
You're going to make mistakes. Anyway, come over here. Let me keep going on this. So this is a pi squared. There's a pi, so pi stays on top. Then I have 2 squared and 2 downstairs, so there's a 2 on the bottom. I got 120, right? I got rid of the pi. I have a 10 to the minus 14. That is complete factor. Then I got an F squared, L squared, I naught squared. And let's just make that 60 pi over 60 right here. With it? And then you're going to have this angular function, sine squared of theta over r squared. So that's P max. All right. This is the power density as a function of both theta and r anywhere. Now I'm going to break it down into one thing, make life easy. When I take that, and I'll do it right here. Okay, well. Power radiated is going to be the integral, double integral of that, all this. So let's try to get some constants down here. So what I'm going to do is take this entire mess right here and just call that K. And so I got K. Then I have sine squared of theta over r squared. That's the average power density. Now I have to multiply by the differential surface, spherical surface. Do you remember what that is? R squared sine of theta d phi. This is the differential. It'll be in the AR direction, but this will be in AR. The dot product will be 1. This phi goes from 0 to 2 pi, and theta goes from 0 to pi. You probably see something coming out of this one. So first, the r squared is canceled. It's pretty straightforward. That cancels. Next, the k I can take out in front. I have k. If you look at this, there's nothing inside that kernel of operation. The kernel of integration, I can hear that it's a function of phi, but I have to integrate from 0 to 2 pi. So now I get 2 pi here. After that, I'm left with this integral. Sine cubed of theta d theta from 0 to pi. At the end of the day, what are you going to get? You're going to get k, and then it's going to be times 4 pi over 3, isn't it? Right there. That'll be total power radiated. Remember, k is this mess right here. So if that's the total power radiated, now I need to find the radiation resistance. You want to take a look at that antenna we have here with the current I naught. And we want to say what this really looks like, because we got a source out here. It's got a voltage right here that's causing this current I naught to occur in this antenna. So coming back to this thing, we're going to model this antenna. The short little antenna has a resistor. So we say that we have some voltage giving rise to some current, but we need what is the effective radiation resistance of that. Well, anytime you got a resistor and you got current, if it's AC current with a peak value of I naught, you know that the actual power, right, dissipated here or radiated in this case, because that resistor is representing the transfer of power from current into photon. That's going to be equal to 1/2 magnitude of I naught squared times R rad. So you take that and equate it to this over here. You'll notice the I squared is going to cancel. Or I should say not this, but the K over here has the I squared. Y'all with me, class? Here's what happens at the end of the day. But this is the total power radiated. Now, if you get the radiation resistance, the I squareds cancel and you get R rad. This is the one you remember. R rad will be equal to, in this case, 80 pi squared L over lambda squared ohms. You see that? For a short dipole, L has to be less than a tenth of a wavelength, right? So if this is going to be, if this is 1/10 divided by, or 1/10 lambda over lambda, that's 1/10 squared is 1/100th, right? 1 over 100 times 80 is 0.8. 0.8 times pi squared, call pi squared 10, right? That's only 8 ohms. That's very little impedance. The implications are you need a lot of current to radiate power with a short dipole. Anytime you need more current, you get more losses because there's a resistance that's inherent to any kind of wire. Whenever you're running current through it, you're going to be dissipating power. That's why with these high power lines, you all have power lines. The whole idea is they like to transmit power with the highest possible voltage, so it'll be a minimal current, because power is voltage times current. Because any little bit of current causes a lot of loss. That's the reason they have such high voltages. And I don't even know what the highest voltage is around here. I don't think they get
500 kV.
They get up to 500. I think it's 750 kV out west. I think that's the highest possible. They get 500 around here.
Element power is 500 kV.
That's high, so that would be out of like a power plant, like Martin Dam or something. A transmission line. You'll never get.
The dams usually don't produce 500 kV.
So that would be a nuclear reactor.
Now
or coal.
that would be 500 combined cycle coal.
And again, this is not my area of expertise, but I know they would like to have it at 1,000,000 volts or more. But the minute you get up to that super high voltage, you get what's called corona discharge around wires. And when that happens, you get a lot of power loss. And you can also get arc open. There's a lot of dangerous things happen with real high voltage. Anyway, that's sort of the trade-off. Back to this thing. This is one of those things you have to keep in mind, that you would like a higher current. You would like to have less current give you more power. In other words, you'd like the radiation resistance to be much higher. That's what a half-wave dipole does. Now, spent a lot of time on this. Here's how a half-wave dipole works. And let me go over here. Remember, this is just a short dipole. We got the directivity, we've got the radiation resistance, we got everything we need to talk about far field behavior from a short dipole. Now, there's one little thing I'm going to say. And we're going to use this to find out the electric field from the entire, for any kind of straight wire antenna. When you have a differential current, say I have a current, but the thing is just got a length of dl, and it's got a current I, and I'm a distance r away from it. Now assume that this thing is at the origin. And here's the angle, theta. Now we're in the far field still. It gives rise to a differential electric field out here in the far field of exactly the same type, J, eta, beta, I, but now it would be dl, and this would be I, and it will be a function of position. I'll just call it I for now, dl, over 4 pi, and then I usually break out the e to the minus j beta r by itself over r times sine theta a theta. You with me? I get that as dE. Now, why did I do that? Because now we're going to talk about dipoles of arbitrary length. So when you have a dipole, this is a dipole, the length of that dipole, L, is now greater than lambda over 10. And it's centered at the origin, so down here it'd be minus L over 2. And here is L over 2. There's going to be a current distribution, call this I of Z, that's on this. It's not constant anymore. You with me? Please just listen to me here. I think this might help. If you look at this current distribution, this is realistic. Anytime you have current, if you think about that, how much current is going to be flowing off that wire right at that point? None. So if you have a wire, it's like a pipe that's capped. How much current flows out, or water flows out of a pipe that's capped? None. The current has to go to 0 when it's terminated like this. Has to. So what you get is a current distribution that's going to look something like this. It'll be symmetric. That's just magnet. it'll have a peak value of I naught here. I mean, this is going to have some maximum value of I naught. But if you were to try to solve mathematically for the current distribution on that, knowing that the radiated fields were going through the whole 9 yards, you're going to find it's untractable. There's ways to do it by doing series expansions and all that stuff, but there's not a simple closed form solution for the current. But what we know it is approximately is the I on any short dipole, or not short dipole, any dipole, is actually going to be of the form of some I naught. This is in his book. You're going to see a sign here, and then it's going to have, the way he does it in his book, he's going to have beta, and then it's going to be he's going to say this I of z as a function of z, it's got some I naught, and then it'll be of the sine, it'll be of beta, and then it's going to be times the magnitude, well, it won't be magnitude, it'll be z minus L over 2, and then he'll have z plus L over 2. You see, which equation is that?
8.67 on page 448.
Now, here's what you have to notice. With that equation, just listen to me. Let's take a look at it. Let's say z is L over 2. That's the length. What is the value of the current?
0.
It's got to go to 0. And what is it at the origin here?
Oh, it's going to be.
We don't know. It depends on the length. You all see this? Now, if you take a look at this right here, if the value of this length from here to here was lambda, if you think about this, if this is going to be, if the length was lambda over 2, then you would see at the origin, that would be the length, you'd get a value of I naught, be the sine of 90 degrees. But if you have a full, if this is a half wavelength, it works. If it's a full wavelength, you get 0, you would get this, theoretically. You don't actually get 0. It should be a little troubling, right? Now, the truth is, if you have a dipole, a real dipole, and it's a half wavelength, you will get a trickle current, but it'll be very low. And the reason is because that, first of all, is approximation. It's not yet, but a lot of this stuff has to do with the thickness of the wire. And the larger the wire radius, the more, I guess, the more perturbed it is from that exact solution. But just do the math on this stuff. You'll have L over 2 minus magnitude z here. And the only reason I'm saying that is, look, when z is 0, you'll be more clear this way, and there won't be a sine function. When z equals 0, I of 0 is going to be I naught times the sine of beta L over 2. Now, beta is 2 pi over lambda, right? So I can write this as I naught here would be equal to, I mean, I at 0 would be I naught, and that's a scalar variable, times the sine. Beta is 2 pi over lambda. There's a 2 there, so it's going to be pi over, and then you can say it's L over lambda. Now, follow me on this, guys. L is the length of the antenna. When L is equal to lambda over 2, I have lambda over 2 divided by lambda is 1/2 times pi is pi over 2. The sine of pi over 2, or sine of 90 degrees, is 1. So when you have an exact half-wave dipole, so when L is equal to lambda over 2, the current distribution on it looks like this. This would be the current. Yeah, this is the, if you take a look at this, if the length of the antenna from here to here is lambda over 2. If you take lambda over 2 and you divide by lambda, you get 1/2. Now this is going to be the value of the current at z equals 0. 1/2 times pi is pi over 2. The sine of pi over 2, or sine of 90, is 1. It's a peak value. It'll look like this if you plot it. as you get higher and higher, I mean, as the length of the antenna gets longer and longer, and you go to an actual value of L equals lambda, you get this kind of crazy. Now it'll do this. Your peak will be here, and the current, if you're applying the current magnitude of current here on a Z, it will go to zero there, that field, which means it would have an enormous impedance, because for any voltage, you're getting almost no current. The truth is, nobody uses a full-length, a wavelength antenna for much, because now you're going to get, when you prove this, you're going to get a couple of weird lobes when you look at the actual radiation pattern for this. This one we don't, the L/2, but I'm about out of time. Here's what I'm going to do. I know we got a long break coming up. There's nothing I can do about that. And I'm going to ask you to do a few things with the reading of some problems. I'll give you problems outside of this book. I'll make sure I give you the answer. But when we're doing this, is all straight wire antennas. Short dipoles are going to have a given impedance that we know, right? We know the power density, we know everything about the D fields, all that stuff. When you get arbitrarily long dipole antennas, they're generally interesting to know about in terms of the field formulations and stuff. But the one that is most important is the half-wave dipole. That's the one everybody uses. And the impedance of that is about 73.2 ohms plus J42.5, but it is a function of the radius. And what I want to do is work through and just finish, when we get back, that straight wire antenna. All these straight wire antennas, and do the small loop antenna. This is in the book on this, right in this area.